This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right. Good afternoon, everyone. It's my pleasure to do today the last lecture with the guest, closing the subject with the guest lectures. I have two great guest lecturers today from IBM Research Australia. The first one is Arun, and he got his PhD from UNSW, and he was a postdoctoral researcher here at University of Melbourne, and we collaborated during that time in Center for Energy Efficient Communications. And now he will tell us, he's been with IBM since...
5.5 years now.
Wow, time flies.
Time flies, indeed.
Yeah, it's like yesterday you joined, so it's been 5 years already in IBM Australia, and then he will talk about really nice things, and then I will introduce Julian, who will pick up and also give you even further perspective. So then after his talk, we will have a little bit time for questioning as well. Yeah. So the
all right, Tansu, yeah, thanks a lot, and yeah, great to be back. Thank you. So I'll present some of the work that I'm doing in the lab, and we call it Beach. Not a good time to be at the beach today, but nonetheless, this is more looking at how do you make buildings more energy efficient from a heating and cooling perspective, right? I hope it's audible. You're all able to hear me okay? Yeah? Okay. So I'll start with a short video, kind of motivating why we are actually doing this kind of stuff. So that is pretty, kind of painted a very grim picture of where we are all heading, right? But there is good news, of course, light at the end of the tunnel. So just a quick summary, what does it say? 2060, the building sector will account for almost an increase of 30% in the energy demand of the planet. It's almost the equivalent of the households in the US, European Union, and China in 2015. That's a lot, yeah? That's the ugly side. Even today, things are pretty bad, right? From that International Energy Agency, the IEA video, 50% of global electricity consumption today is attributed to buildings, right? And there was a study in the US which said that almost 90% of our time is spent in built environments, right? So that's worldwide CO2 emissions, 25% is attributed to buildings. And for everyone who watches the good, bad, and ugly movie, there is always a good sign, right? So if you actually do things really well, there is a good future, right? From various different perspectives of trying to keep building energy consumption down, okay? And that's essentially the work that I've been doing. So why is it so important? So why do we care about buildings, right? So many of you, well, at least hopefully most of you would have heard this term called HVAC. So basically what HVAC stands for, as it's there, is the heating, ventilation, and air conditioning systems that basically provide all the climate control in the space like you are in, right? This provides cooling, provides heating. At home, you have your air conditioners and so on. So this equipment apparently is one of the largest consumers of energy in buildings, particularly in commercial buildings, right? And this is a very interesting statistic. In 2015, the total electricity bills that all the buildings paid in Hong Kong was almost $1.57 billion US. That's a lot of money to be spending on electricity bills, right? Well, that's where we come in, try to reduce all of that. So in the rest of the kind of short presentation, I'll focus on a real-world application of the work that I'm doing for a specific building here in Australia, right? So we are looking at the building. It's an office building. Anywhere between 300 to 350 people use that every day, and they pay a significant amount of money in terms of electricity bills, and they have a mandate to kind of improve their energy footprint, keep the energy emissions down, CO2 emissions down, and so on. So we're trying to help them with that. And this plot basically shows the energy or the power consumption of that building in a hot day in December, probably 15th, 18th of December or so. The red one is the main supply. That's the meter that they actually get billed on. And they have a bunch of sub-meters where they can actually profile the power consumption of the chiller. So this is in northern Australia in a place called Townsville, which is just around Cairns, 400-500 kilometers south of Cairns, I think. Whatever. And they have a bunch of chillers. Now the chillers are these big beasts that provide the cooling for climate control, right? And they consume a significant amount of power. So they have two chillers that you can see in the two curves there. But the most important part is this little dotted line. That's the total power consumption ascribed to the chillers alone. And if you look at it, in this particular building, and by and large for pretty much all large buildings, these HVAC system accounts for almost 40%, if not more, of the power consumption. So there's clearly a reason to keep power consumption of these systems down to make the world a better place. But how do you do it? So that's the problem, right? How do you do it? If it was so obvious, they would have done it by now. It isn't, and I think that's where we are trying to add new ways of doing it. And the approach that we take, the solution is Beach. So basically, it's a kind of a data-driven solution, right? So data-driven because a lot of these buildings are instrumented with a lot of different sensors. Even here, you can see a temperature sensor on the wall on the far right that is probably logging real-time temperature in the space. I think this is kind of spread probably in most places. I'm not sure if it's just one here, but you have the cooling coming from the roof. These temperature sensors record what's the temperature inside the place, and that gives an indication of comfort. The question is, can we use all this data that's being generated by these sensors to kind of smarten the way the buildings operate, right? The so-called data-driven analytics. So that's the kind of approach that we have taken. And we combine that, all the building sensor data from what is called a building management system. Right? Think of it like your operating system, your Mac or Linux or Windows. So there's a similar kind of a building operating system, a building management system that gathers all this data, but surprisingly does very little analytics. It doesn't really use it to drive efficiency stuff. It's kind of the very rudimentary analytics is what it does. But if you combine all that data that's being collected and bring in the electricity rate structures, right? Buildings have various tariff cents per kilowatt hour, all the stuff that you pay at home, you can actually do a kind of a recommendation solution, basically telling how you can operate the buildings differently. And that's what we've done so far. So broadly speaking, the box in the bottom left does some kind of a modeling of the thermodynamics in this space. So basically look at the heat flow and temperature evolution. We take all that modeling, put it into an optimization framework, do some machine learning in terms of forecasting occupancy and so on, and then come up with a recommendation framework which we have deployed, and it controls the building in real time. So completely agnostic to the type of system that it's running, does not require any human involvement, but we've taken it to the level where we directly control the building. And I'll kind of quickly show you what we've done. So as a first step is how do you model the temperature evolution in this space, right? And this is just a floor plan of one of the sections of the building. They got various different zones, as you can see here, in different color coding, and they have various temperature requirements. But let's say you pick data from this particular zone, zone 5. Think of it as this is the space, this is a zone. You have all the temperature sensor data, you have the chillness of the air coming in from the roof, and you have an indication of the occupancy. So with all that stuff, you can kind of build a very simple kind of a thermodynamic model using the first law of thermodynamics. And basically, what does it say? Right? What does it basically say? It says that the rate of change of temperature, Tz as a function of time, is kind of a function of 3 or 4 essential parameters. Right? One is the effect of the ambient. The heat flows from hotter places to colder, so the temperature around the periphery of the building is one of the parameters. The internal heat gain, so people like you and I, we are here, we contribute heat. All the lighting, all the other computer stuff, That's a source of internal heat gain. And there's another last component, which is basically the cooling provided by your air conditioning system, basically the cold air that gets pumped from the top. And that removes the heat, essentially. Right? So these are, at a very high level, the most important kind of parameters that model how the temperature is influenced in a specific region. And once you apply this and you can figure out, then you can kind of start comparing the efficacy of this model. And I call it a gray box model, but you can nonetheless figure out how efficient it is. Is it useful? Is it useless? And so on. So this graph is one of many to validate this approach. And what it basically shows on the y-axis is the zone temperature in this particular section here, zone 5, for a particular day in the summer as a function of time. So this building is an office building, typically is occupied from 7 a.m. to 5:30 p.m. Right? It shows two curves. The red one is the actual temperature recorded from one of those sensors, and the black curve shows the temperature predicted by this gray box model. Right? It basically shows that you have a pretty good accuracy for how things are likely to evolve in this space. So the root mean square error here is 0.1 degrees, right? So that's pretty good. So we've kind of done this over multiple days, multiple different sections of the building, and by and large, this model shows a very good handle for modeling the temperature evolution. So once you do this, you can take it to the next step, where you take this thermodynamic model, put it in an optimization framework, taking into account the electricity rate structures and so on, and the objective is basically to reduce the cost of cooling a building. Right? Keep the costs low as possible, but people should be nice and comfortable, right? So this naive thing to do is just turn the damn thing off, you'll save everything, but then obviously people are not comfortable. So how do you kind of get that balance? That's what we do in the optimization framework. So forget about the details, but just at the high level, the objective here, the objective function that we want to minimize is the cost of electricity to cool a section of the building and therefore the whole building, right? And there's a kind of bunch of constraints that we need to adhere to for the time the building is occupied, say from 7 a.m. to 5:30 p.m., right? And that's what this K represents, basically. So what are the constraints? The first constraint is that the thermodynamic model should hold, right? So we should be able to figure out what is the temperature at time step k plus 1 if you know the temperature at time k. So it's kind of a recursive equation, but that has to hold. Otherwise, you are not able to model the evolution of temperature, right? So that's one of the kind of the constraints. The second one is how much cooling is actually provided to cool the space, right? How much cooling is provided by your HVAC system is another important parameter that we need to capture. And there are different ways you can do it. And here is just one way. This Q.cool is an expression to characterize the cooling provided by your HVAC system. And the last constraint, of course, is the comfort, the thermal comfort constraints, right? So you want the space to be within an acceptable temperature, neither too hot nor too cold. And you're kind of implicitly modeling the comfort of the occupants. So think of it like, if the space is occupied, then the temperature should be guaranteed to be between, say, 23 to 25 degrees Celsius, as an example, right? So these comfort constraints can be provided by the building manager, by the building codes, and that can all be populated here inside this optimization. And this term E of K is basically the electricity price, the tariff that the building is subscribed to. Okay? So you can do this and try to figure out how useful it is. What we have basically done is taken all that solution and hosted it on an IBM cloud platform. So basically this entire beach stuff sits on our data center in San Jose and is almost 12,000 kilometers away controlling a building in Northern Australia, completely in real time. There's really no human involvement at all. It decides when to turn off, when to turn on the chillers, various sections, how do you change the temperatures so that people are comfortable. So all that stuff is in the cloud. And clearly you want to have a secure way of talking to a building, right? You don't want to, for cyber security reasons, obviously. And what we do for that is, there's an emerging standard called Project Haystack. And if you haven't seen it, I'd probably encourage you to. It's got heavy backing from universities, industries, and they have a very nice representation of IoT devices. So basically they give you a kind of a nomenclature for addressing various IoT-enabled devices in any space, any building, for example. Could be temperatures, could be your chiller, your boiler, your camera, whatever it is. It's a very systematic way to do it. And the most important thing is it uses RESTful APIs. So for people who have done web programming, it's as good as just issuing a REST call to control the stuff in the buildings, completely transparent to the user. So that's what we've done, and those REST calls actually controls that building management system. So we override all the default settings, and adjusting the building management system in turn adjusts the HVAC of the building, and in real time we are able to close the loop. So we can do those GET APIs, keep pulling data off the system to make sure we are all doing nice and cool stuff, right? Not that the building is frying or it's excessively chilled or anything. So you can actually monitor in real time. And this has been running for the last 6 months. And here is just an example of the trial that we have been doing, comparing Beach with their baseline mode of operation. So what you see here on the y-axis is the power consumption of the 3 chillers in the building for a particular day. This is, I think, the 2 days are here, 6th and 7th of March, from 6 a.m. to 5:30. 6th of March is the baseline. So assuming the building did not do anything, they just ran business as usual. 7th of March, we did the experiment, and the difference you can see is that is about 15 to 20% reduction in the energy consumption for cooling the building. And there was no thermal discomfort reported by anybody. So no one called us and said, hey, what are you doing? It's so hot, kind of stuff, right? So people were comfortable. They didn't even know it was running. And on an average, the month of March, April, we're seeing anywhere between 15 to 20% savings in energy consumption and electricity costs. And just to give you an idea, this building is, I think, pays about $400,000 a year for electricity bills. 40% is cooling, so 160, 20, 15% of that, you can figure out the numbers, right? It's not 30, 40,000, which is pretty good for one building, right? And these places, people have hundreds of buildings, and if you put it all together, I think there's significant merit in driving savings, improving footprint, while making sure that people are nice and comfortable, right? And for those people who really want to know more, there's a bunch of papers. I'm sure you don't want to read any of that, but if somebody who does want to read it, this is available for you to go through it. So I'll stop with that, 15 minutes, 5 minutes for questions. If you have any, happy to share.
Yes, we have time for questions.
Yes? How much does it cost to install that system? That's a good question. This is being recorded, I cannot tell you. No, the beauty, yeah. So what we basically say is that you don't need to do any retrofits in a building, right? So if you are running a building, I don't want you to install any new sensor. I don't want you to have data for months and months. So basically, the model will learn on the fly. With 1 day's worth of data, we can get this running, and we can work off the system that is already installed in the building. So the capital expense to run Beach is almost zero, right? The operating expenses, well, it runs on the IBM cloud, so there's a different pricing model, but in principle, it is negligible compared to how much they pay in their annual electricity bills. Yes?
So finally, this task is to actually give the comfort level, without changing the comfort level of the people who in the building, isn't it? So while doing that, keep the money cost lower.
Mm-hmm.
So why can't we do it just simply that keep the temperature constant and use the inbuilt the temperature controller to turn off or turn off the machine, or just to let it run out? What's the difference between that and what are the variables captured in this model?
Yeah, so I think 2 key differences. One is we are doing a lot of forecasting, right? So we are trying to model how the space will evolve, let's say, over the next 12 hours. So for that, you need to forecast outside weather has an impact on the place. You need to forecast occupancy. So imagine if you have just 20 people here, cooling this whole space thinking there are 100 people doesn't make any sense, right? You're kind of excessively cooling it. And the third thing is keeping the temperature constant is also not necessarily a good thing to do. You have to change the temperature for comfort, but the key thing is how do you actually change it, right? You need to smoothen the cooling load. There's a function that you actually smoothen, so you gradually cool over a longer period of time, and that's where forecasting of all these quantities come into account. Therefore, it is a lot different than just putting a simple analytic sitting locally, which is what they do today, right? That's what they do. They keep the temperature constant today, which doesn't make much sense.
So there is a pre-cooling involved here, right? Some of the gains come from pre-cooling?
Right. I didn't show a lot of the charts. So the other point that Tansu said, right? You don't need to start cooling at exactly the same time every day, which is what most people do. So the optimization will determine should you start pre-cooling. So basically, do you cool in advance of people arriving, or do you kind of cool a bit later because the space is already nice and comfortable, right? So these kind of decisions can be more systematically obtained if you run this framework rather than some ad hoc rules-based kind of approaches. Yeah.
How do you know the internal heats without sensor?
There is a sensor, right? So there is an internal zone temperature sensor that we use.
The sensor in each room.
Yeah, in fact, that's a sensor in this room.
So the sensor measures the temperature.
Yes. So the sensor will record the zone temperature. So let's say it is probably 22 degrees now. That sensor would be recording it. So you can now convert that temperature readings into a measure of cooling. I mean, that's using a well-known expression. It's there in one of those things.
So what's the difference between the home use conditioner? For example, it's same thing.
Yeah, conceptually it is the same, right? So what you would do at home is you change the temperature on your air conditioning system. That's called a set point. What is the temperature you would like desired in the space, right? That is what we actually dictate. What should be the desired temperature in the space, which meets the comfort guidelines and yet keeps the costs low.
Okay, so what do you mean for the prediction temperature?
We predict the influence of the outside temperature of the weather conditions on the certain space. So if you have an office building, we have windows, the space close to the window can be hot if you're kind of facing the sun, right? So what we forecast is the implication of the outside air temperature on the internal temperature evolution. So that's a quantity we forecast. And the second is we forecast occupancy. Right? You don't want to unnecessarily cool the place if you know that there's 10 people relative to 50 people. So there's a comfort trade-off that happens there.
So you use the data from the sensor?
Yes. We use the data, so we build model from historical data and use that to predict over the next time period. So over the next 12 hours, for example. That's what we predict.
A question regarding occupancy. You don't have a sensor for occupancy, right? So you do it implicitly through the temperature variation in the room.
Well, good point. So in this building, we don't have people count sensors. I use carbon dioxide sensors as a proxy for occupancy.
You use an extra sensor for that.
Yeah, so they have CO2 data because of building codes. There's a requirement that CO2 does not exceed a threshold, but it's a proxy for occupancy. So we leverage those kind of data.
So, yeah, maybe last question.
Does this technology need to cooperate with a smart grid? I mean, if it is widely used, then maybe it will impact the power system security.
Good point. It will reduce the load on the grid to provide the amount of demand you require because you're fundamentally lowering the requirement. The implications of what that will happen at a grid scale, I have not really thought a lot about, but that's a nice point. Worth definitely thinking about.
So to put to perspective of the subject, so you solve an optimization problem. The optimization obviously kicks in there as a constrained optimization problem, right?
Yes.
And then machine learning is used more in forecasting.
Exactly.
Providing the optimization.
Exactly. Providing the inputs to run the optimization.
That's a good combination. They are supposed to be able to do this now. Okay. No,
Well, test them with the exam.
Thank you very much again.
Thank you.
So while Julian is taking the mic, I would like to now introduce our second speaker, Julian, from, again, IBM Research Australia. He got his PhD from Oxford University, UK, and he has been with us at University of Melbourne in a nice electrical vehicle project, multi-years as a postdoctoral research fellow here, and then he moved, just like Arun, to IBM, where he continues doing really interesting research and great projects. Thanks for coming today.
Thanks. All right, great. Yeah, thanks everyone. Thanks Tansy for the invitation. It's really nice to be back. Like Tansy said, I used to work on electric vehicles and their impacts on the grid. And then I joined IBM also about 5 years ago, and it was kind of a natural transition to go from batteries on wheels to batteries in people's homes. In fact, in some ways, they're similar. So I'm going to talk mainly about optimizing the value of energy storage. So energy storage, today I'm going to talk about specifically batteries, and I'm going to use a use case which is a residential use case. So when you think about people who stick a battery in their home, it's a really huge topic here, especially in Australia at the moment. And you sort of think about it, you're like, well, a battery is a pretty simple thing. You charge it, you discharge it. What's the big deal? And so that's what we thought initially as well. And we looked at it and we're like, well, how much value will these batteries really provide? And we did this initial really basic study, and pretty quickly we realized it actually makes a huge difference about when you charge them, when you discharge them, which rates you charge and discharge them at. And because you're trading off multiple different value streams, and because you also have to take into account the impact on the battery. So this is all about optimizing the value you get out of batteries. Just to get us started, who here has heard of the Tesla Big Battery in South Australia? About half of you. So in Australia, we have the world's biggest battery. It sits out in the desert, about 300 kilometers north of Adelaide. I had a chance to visit it last year. It's actually not that exciting. You get there, and there's just a bunch of containers in the desert. But what it's doing is really, really exciting. It has totally outperformed people's expectations. It can ramp up and down in milliseconds to stabilize the grid in that part of Australia. And it's kind of a revolution that's happening right now with energy storage going in. Anyway, this big battery, just like batteries you stick into your home, are still pretty expensive, and the only way that you can make them pay for themselves is to use them for multiple things. As in, you need to have at least 2 or 3 value streams, 2 or 3 ways to save on your bills or somehow create revenue. So I'm going to go through an Australian residential use case and spell it out really, really clearly. So here is one of the homes we're studying. It's got solar panels on the roof. And here are some typical profiles for this particular house. Let's see, what does my mouse show? Yeah, there we go. So up here, the red line shows the electricity demand, how much electricity they're using. It's fairly high in this house. And the green shows what the solar panels are generating throughout the day. Then here I'm showing the price. There's one price that you pay to buy electricity from the grid. That's the purple. And most people pay a peak and off-peak. So you pay maybe 40 cents during the day and 20 cents overnight, or something like that. And then I'm not sure what color that is, cyan or blue or green. But this shows what the price of the wholesale electricity price was. So that's the price at which generators could sell their electricity on the electricity market. So people in their homes can't actually participate directly on the wholesale market. But there are now ways that you can get paid for discharging your battery to the grid when it's good for the grid, when it's needed in the grid. So this is the use case. This person, this owner of this house with these panels, they're thinking about installing a battery. What will a battery do for them? The first obvious thing, and that's probably the thing that everybody thinks first of all with batteries in homes, is solar self-consumption. So your solar panels are generating all day long while the sun is up. Half the time you're not even home, and all that energy just goes back into the grid. And if you're not getting paid much for exporting to the grid, you're kind of losing it. So really, if you could store all that solar energy in a battery and then use it to offset your demand later in the day when you get home and you turn on your TV and your microwave and your kettle and everything else, that's one way to save on energy, or sorry, save on your bills. So if you had a battery, if you had a battery in this home, this is what it would be doing if it was doing only solar self-consumption. Here during the day, as the sun rises, it starts to charge. Then as you get home, you start to use electricity, you discharge. The next day, again, during the day, it charges, a little fuller this time, and then as you get home, it discharges. That's one thing you can do. Another thing you can do is tariff optimization or price arbitrage. So that's basically charging your battery when the price is low and discharging it when the price to buy is high. So overnight, you pay only half as much, say, as you do during the day, and this is what your battery profile looks like when you do that. I lost my mouse. So let's say you charge your battery overnight when it's low, when the price is low. And then when you go into the high price period at 7 a.m., you start to discharge your battery to offset your demand, and it's totally empty already halfway through the day. And then as soon as you hit the low price period, you charge it. And then as soon as you hit the high price period, you discharge your battery. That's another way you get value out of a battery. And then the third one, which is pretty new, and Australia is the only place, as far as I know, in the world where some energy companies are now actually allowing or incentivizing this to happen, is where when you get spikes in the electricity market price, that's a great time to discharge to the grid. It means that your energy company doesn't have to buy very highly priced electricity from the market. So if you only discharge your battery to the grid when it's really desirable, then you have this is how it behaves. You have a fully charged battery. There's a couple of spikes in this price here, so then you discharge. Then when the price is low, you charge it again. Then here's actually quite a big spike in the wholesale market price. That's a great time to discharge your battery, and it's empty, and then the next night you charge it again. So if you look at all three of these value streams, and you look at how they make your battery behave, these are three very, very different profiles: solar self-consumption, tariff optimization, wholesale market participation. And the obvious question is, can you do all three of them? And can you do all three at the same time? And now that you all know how to optimize, yes, you can. So it's actually not that difficult. It's a fairly straightforward optimization problem. You're throughout your horizon, in this case 2 days, you're trying to find the best possible way to charge and discharge your battery that saves you as much money as possible on your electricity bill. So a straightforward optimization problem. Probably some of the techniques Tanzu has taught you, probably many of them would be applicable and you could apply them pretty directly. There's no sort of one technique that you have to use for this kind of problem. In our case, we ended up going with a method called stochastic dynamic programming. I don't know if you went into dynamic programming at all. But basically, in short, dynamic programming means that you kind of try to find, you look at all the possible paths you could take from now to the horizon, and you find the best possible one. And I'll go into just a little more detail since I do have the time. Usually when you see dynamic programming explained in a paper or in a textbook, it's often explained in terms of recursive equations. But for me personally, I find it much more intuitive to think of it as a grid. And all your states can be represented in this grid, and you're trying to find the line through this grid that gives you the best solution. So in this case, you can represent state of charge of the battery. You discretize it, so you have state of charge 0%, 1%, so on, 100%. And then you have your time intervals over which you're trying to optimize. And then you can calculate from any of these states, say 1% state of charge at the end of your horizon, to 2% state of charge, how much you're either winning or losing, how much you're getting paid to export or how much you have to pay to import. So you can go from your very last stage of your horizon, and you can work your way through bit by bit by bit for every single square in this grid, keeping track of whatever the best solution was to get there. And I'll go all the way to the beginning to where you are now and keep track and say, okay, I realize now that for me the best possible way to minimize my electricity cost from here to 48 hours from now is to go this way, this way, this way, this way, charge, discharge, charge. And it's actually, when you write it out, it looks like this. But if you actually want to implement it, it's just 3 for loops in a simple program. And we don't even use oops, I lost the mic. We don't even use a sophisticated library or anything like this. It's actually quite simple to just program it from scratch. So just to describe what this is, basically, cost to go is how much it costs to get to any particular box in this grid. You're trying to minimize that, and the state transition from one state to another is based on your forecast demand, your forecast generation. If you're importing from the grid, the total amount you're importing times the cost of that. If you're exporting to the grid, the total amount you're exporting plus the reward of that. And in this case, it's negative because you're actually getting paid. So yeah, it looks kind of complicated when you write it out like that, but it's actually not. Once you dig into it, it's pretty straightforward. So just a simple result from some early work we did. We looked at a data set of 100 houses in New South Wales, and we said, okay, most of these systems today do pretty basic stuff. They just charge to a certain percentage at 7 a.m. Then they do solar self-consumption. Then they basically don't do anything smart. They don't forecast. They don't optimize. They don't do anything. So if you do that, you get sort of 55% of the total possible value you could have had. Now the green is the total possible value. It's the best possible solution you could have had if you were God and you could forecast exactly what the sun was going to do and you could forecast exactly how much electricity demand there was going to be. Green tells you that the maximum possible value you get from the battery. So really most systems today are only kind of getting 55% of the maximum total. Now you're never going to get the maximum because forecasting is difficult. You're never going to get it exactly right. But even just with a few simple forecasts and doing a few basic things, we can do much, much, much better. I'm not sure what the percentage is, but probably about 20%. Yeah, roughly 20. By doing a very basic forecasting and optimization, you're actually getting 20% more value out of your battery in that particular, in just 1 year. And if your forecasts are better, and that's something we've been working on, then you can even do much better than that. So, just going to check here. I guess I've got 5 minutes left. So instead of, I'll just briefly mention, we've done all this work, we've done the research. When you use data sets and you run it in simulation, everything's really clean, and the results are very promising. And then you take it onto real systems, and then all of a sudden you realize that there's big gaps in the data, and you have communication issues. You need a router in that house to connect to, but then the woman living in that house doesn't like the lights flashing on the router, so she turns it off. And you only realize it 3 days later, and you're like, there goes 3 days of data. So all kinds of things happen when you try to roll this out in reality, which you have to account for. If you want it to work, you have to make it robust enough to deal with dropouts and gaps and latency and so on. But somewhat similar to how Arun is doing the buildings work, we are doing this as a cloud-based service, where basically whoever goes and installs a battery, whatever company it is, whatever installer, they sign up for the service, and really just every half hour or hour they call the latest solution and they implement the latest solution in the inverter. And it just does this clever thing of choosing the settings in the inverter so that you're saving as much money as possible. So one thing I pointed out in all this was that how good your forecasts are is really important in terms of how much value you're getting out of your battery. So forecasting electricity demand is pretty hard. It's quite hard to know when people will be turning things on. You can get close, but getting it exact is difficult. Forecasting solar generation is also not easy, but it's a little more, there's more sort of pattern to it. But when you get down to individual homes and solar panels installed on rooftops, every single location has a very different profile. This is because of the way that the panels are facing. There might be a tree growing there that casts a shadow certain times of the year, but not others. There might be a chimney. Somebody's panels might have gotten dirty. All kinds of things start to happen, which start to affect your forecast of solar generation. So here's just an example of how different 3 houses generate solar energy. This one is somewhat east-facing, but it has a pretty normal profile over the course of a sunny day. The red is the peak. But in the winter, or late autumn, it has this kind of profile. And you wonder, why would it have this really nice, clean profile in summer, and then all of this stuff happening in winter? And that's because there's a tall building next door, and because of the angle of the sun in winter, all of a sudden you miss out on that morning generation because of the shadow that's cast by that house, but it's only cast in winter. So your forecasting model needs to adjust over time to these things that are happening. Here's another one, pretty standard shape to the profile, but if you look, the peak is at about 2:30 p.m. instead of noon when the sun is highest, and that's because these panels are facing slightly west, so generation is shifted a bit to the afternoon. And then this one is really interesting. There's one set of panels on the garage and another set of panels on the roof. And before I saw the rooftop, I saw this data, and I kept seeing this bump here, and I thought, what is going on with this house? What does it have on the roof? But that is basically the result of having 2 sets of panels. So keep losing the map. So these ones are north-facing, and they generate more in the morning. But as the sun goes overhead and kind of gets over the edge of this rooftop over here, then the west-facing ones take over, and they provide the bulk of this generation. And in summer, the peak comes from these slightly west-facing ones. But in winter, because of the angle of the sun, the peak comes from those north-facing ones. So again, it changes over the season. It's totally different shape from the other systems. And so when you want to forecast a house's solar generation, you can't just say, this is the angle of the sun, this is the time of year, this is how much solar radiation there is. You actually need to know about that system. What's the shape? What's it doing? What's happening locally? So we don't really, if we want this to scale to lots and lots of houses, we don't really want to build a physical model of every single location and have a lot of effort involved in setting up the forecast for every single one. So we thought, how can we scale this up in a quick but effective way? And so we're doing just a combination of machine learning and a simple data-driven technique, which is basically you take a look at a whole set of days and you take the maximum value at any interval, and then you run a little filter over it. And it gives you this typical shape for a particular site, which it just gives you some sense of what that system would generate on a completely sunny day at that time of year. And then you can convert that into a machine learning problem. So up here, the blue line shows what the system actually generated. The orange is this characteristic profile, this shape that we've determined for that house. And if you take the difference, it gives you the residuals. It basically gives you a trace of how far from your maximum expected generation you were. And then if you start logging weather data at the same time, like dew point, humidity, temperature, UV index, whatever is available at the site, which might be other things as well, you have a standard machine learning problem. You have a bunch of features, you have an actual, and then you can start throwing machine learning methods at it. And so we've tried this. We've tried 5 or 6 or 7 different techniques. In the end, for us, a very simple standard linear regression gave us a really nice result. And what you do is you keep track of this data. You keep track of your historical data. You build this model, and you have to always retrain it because this is constantly changing throughout the year. You use that model to forecast these residuals, and that in turn then tells you, once you add it to the profile, what your solar generation will be for that site. So simple but effective machine learning problem. And we've just by doing this data-driven thing of seeing for each site what that site is generating, this kind of characteristic profile, we've seen huge improvements in forecasting accuracy for a number of standard techniques when we use it versus when we don't use it. But ultimately for us, so far, this is still ongoing work, but so far we've found that just simple linear regression worked really nicely. So 1 optimization problem, 1 machine learning problem. Thank you very much.
Thank you very much. Questions? We have time?
Similar thing to what someone said to Aaron. If this is implemented in every house across Australia, would that have any implications on how it works? So, like, would it improve forecasting? Would it reduce the peak costs if you were to sell it back into the grid?
Yeah, great question. Again, really good big picture question. So we've only looked at it from the point of view of the person owning the battery, whether it's a homeowner or a commercial industrial or something like this. And we're just trying to save that person money. But that would mean if you do this for all of them, thinking only selfishly, you could have some weird things happening in the grid for sure. That they all start to charge at the same time when the price drops, or that they all start to discharge when the price goes up. So at the scale we're at now, I don't think we need to worry too much with the number of systems that they are at. But definitely, if many people start to install these batteries and they all start to behave in the same way, it starts to become a problem. And then you have to make sure that there are other incentives to make sure that you stabilize the network and so on. Batteries are incredibly useful tools, and they can benefit you, who owns them, behind the meter, but they can also do so much for the networks. So it's actually a huge ongoing discussion in the industry right now, is how do you take batteries, how do you set up systems and set up incentives and tariffs so that people who own them benefit, but they also help with managing the networks. Yeah.
Actually, to add to as a comment, one of my ex-PhD students now works for a utility, and very forward thinking. They were thinking if everyone has an EV and they start to charge at night, suddenly we will have at night peaks.
Yeah.
So they've started speculating about it.
Well, we actually saw this in the project that I worked with you on with electric vehicles. When I was looking at some energy data for some networks, you would see this spike around 6 p.m. when everybody gets home, and then it drops off. And then at 11 p.m., this almost equally big spike, because that's when you drop into off-peak, and everybody's hot water systems are programmed to turn on. So there's like a peak at 11 p.m., which then you have to, the network operator has to handle and take into account.
But there are good news about that. Most wind farms are very effectively working at night. Also coal plants, so they can. There's a lot of generation at night. Other questions? I have one. I really liked your dynamic programming slide. I'm going to adopt it. This
Sure.
matrix
Yeah,
version. So I'll create a slide for that.
Yeah.
So you haven't used model predictive control, right? That would be an alternative way, maybe.
Actually, we do. Sorry, I should have said that. So what you do is you do this dynamic programming. You solve this best possible solution for the next 1 day or 2 days, whatever it is. Actually, for us, even though I sort of showed 2-day horizons, mostly we look only 1 day ahead. you get your solution, you implement the first step of that solution, and then, because things might change, your forecast might get better, it might be sunny when you thought it was cloudy, and so on. So then you go forward an interval, and you completely recalculate the whole solution for the next 48 hours, the next 24 hours, and you implement the first step. It's just like we did with the EVs.
But this is sliding window. Still, you solve the dynamic programming explicitly.
Yes, you're resolving it every time.
But
Resolving
you're
the whole
not
thing.
solving it as an MPC where you stack up and solve it as an optimization problem blindly.
Yeah. Okay. So
You're not doing that. Would be an alternative,
yeah,
right?
yeah. No. So I guess sliding window is maybe a better way, or receding horizon.
Receding horizon or sliding window, which means the same thing.
Yeah.
But you solve explicitly the dynamic program, which is a great example of
Yeah.
dynamic programming. I haven't covered that much
Yeah.
in this subject,
Yeah.
unfortunately.
One other reason we chose dynamic programming was also that, which I went over pretty quickly, was that the way you run these batteries really impacts their longevity. And if you're trying to, so over 24 hours, you're trying to run them hard to get value out of them. But if you run them too hard, then they'll only last you 5 years instead of 8 years. So there's a bit of a penalty too, that you avoid extreme states of charge, which is where they age faster, and that you don't charge them too fast and discharge them too fast. So actually, even though I went through it really quickly, there's a penalty term. When you're running it really hard, you actually can take that, in a dynamic program, you can take into account a model of the battery, which is often super nonlinear, and therefore difficult to express in many types of optimization. But in a dynamic program, it's easy. You plug the model battery into how you calculate the cost going from one state to another. It also means you can easily plug in and out different types of battery models, because different types of batteries have very different characteristics. So that's why we chose dynamic programs.
It's much more advanced. No one? I will ask one more last question. So you used for the machine learning part, you used all the nice classical methods, and it shows the power of classical methods. I must have said during the lectures that don't jump to the latest shiny thing. The old methods often work quite well, as proven.
Yeah.
But you haven't used these latest deep neural network methods like LSTM and recursive neural networks and so on. Did you try? Did they perform?
I haven't yet. It's an ongoing work. Definitely in solar forecasting. LSTM sounds really interesting. So it's one of our interns, also doing her PhD here, actually, is working on LSTM for time series. So yeah, it's a great topic.
Sometimes all these sophisticated is just an overkill, and you get a beautiful solution with.
Of course.
Yeah.
I'm also curious whether the pre-processing that you are doing with the profile, average profile, then you subtract and you forecast the residue, which is a great way of doing pre-processing normalization. Whether and they always claim in deep learning, you don't need to do anything, just give us the raw data, we will perform. I'm curious whether it will really perform or not.
Yeah,
or whether it will better do after the residue.
Yeah.
Because you have a great example.
Yeah, no, I think that's a great, super interesting question. Yeah, absolutely.
Yep. Maybe last
Can
question.
we use this for other energy storage technology? Because I guess if we use that, for example, if you discharge or charge a battery frequently, it may be impact its life. So can we use it for a pumped storage plant?
You mean the way that we solve it with the dynamic program and all that?
No, I mean, if we use this technology, it may be impact the battery's life.
Yes.
Because you discharge and discharge it frequently.
Yeah.
Can we use it for other energy storage technology? For example, pumped storage plant, power plant.
Yeah, I think if you were to go, for example, to pumped storage, at that point, so with the battery, the decision variables, what the levers you can change are how much you're charging, discharging the battery at any point in time. It's that simple decision of what are you charging. With pumped storage, I guess you're starting to look into how much are you pumping and how much are you releasing. So it's probably, I'm not sure, but I would guess it's probably pretty similar in that respect. And then ultimately, the way that we structure it is you have an optimization. In our case, we're minimizing the bill, but it might be minimizing voltage fluctuations or whatever. Whatever the optimization is, you can plug that in, and then you use exactly the same methods with dynamic programming to see what would be the best ways to pump or release over the horizon. So yeah, I think it would be applicable as well.
Thanks
Great.
again.
All right, thanks. Thanks, everyone.
Thank you very much again. I will ask Julian and Arun for the slides if possible. If IBM also agrees, I'll try to post them in. And the last words of the lecture: don't forget your SES forms. I will be in touch via email announcing stuff. The consultation hours until the final exam. And, workshop 4 submission, I put it there. That will be this Sunday. Workshop 3 marks will be hopefully by Monday at your hands, and then mid-June the workshop 4 marks will be by you. So well before your exam, you'll have the full picture. Right? So good luck.